Handling 1 million HTTP requests per second is a staggering volume of internet traffic. Successfully managing that flow puts a company in the same tier as AWS, Netflix, or Uber. At this scale, a simple programming mistake becomes a massive financial drain. Code that functions perfectly for a few thousand users can burn through tens of thousands of dollars in a single afternoon when applied to millions. We wanted to test if we could reach this milestone by simply buying our way there. We rented a cloud server with 128 processing cores and 256 gigabytes of RAM, a machine that costs over $20,000 a month to run. We configured a second beast machine to act as the tester, generating a simulated tidal wave of traffic to see if our supercomputer could hold up under the pressure. Throwing raw power at the internet is about to prove a fundamental rule of engineering. Physical limits will always expose the flaws in your architecture. We began the test with a simple "hello" text response. Despite the hardware, the system hit a ceiling at just a few thousand requests per second. We had hit our first bottleneck, the CPU. Look at the 128-core grid of our processor. Only one core is actually working to handle the incoming data, while the other 127 sit completely idle. Most server software is single-threaded by default, meaning it can only use a fraction of the hardware you've paid for. To solve this, we used multi-threading and clustering, techniques that allow the software to split the incoming workload across every available processor simultaneously. By clustering the application, all 128 cores process requests in parallel. This configuration allows the CPU to handle the volume, but as soon as we sent actual data instead of simple text, the system hit a new wall at 100,000 requests. This wasn't a software failure, it was a physical one. We had reached the capacity of the network pipe. Pushing a massive 6 gigabytes of data per second physically fills the capacity of a standard server's network cable. No matter how much processing power we have, the wire itself cannot carry more data. To move past this, we migrated to a specialized server equipped with a 600 gigabyte per second network card to clear the physical congestion. Widening the network pipe only pushed the system faster toward the most common bottleneck in modern computing, the database disk. For our third test, we introduced a Postgres database to simulate reading and writing actual user data. Performance immediately collapsed, with the system grinding down to 35,000 requests per second. The database was struggling with inefficient math. Computer scientists use big O notation to measure how much work an algorithm has to do as the amount of data grows. When we asked the database to find a random record in a pool of 10 million, the algorithm was forced to check every single row sequentially. This creates a massive delay, making even the fastest hardware feel sluggish. Expensive hardware cannot save an application if the underlying math is telling the processor to do the work the slow way. Even with optimized math, we still faced the physical reality of how data is stored, spinning disks. Physically writing data to a hard drive involves a mechanical delay as the system waits for the storage medium to respond. This latency is a hard limit imposed by physics. Trying to solve this with money is incredibly inefficient. Faster database disks added $1,500 a month to our bill, but only provided a minor boost in speed. High-scale systems solve this by using in-memory storage, specifically Redis. By moving the entire database into the server's RAM, we bypass mechanical storage entirely. Data transfers in memory are thousands of times faster than writing to a physical disk. We ran the final test with a clustered Redis setup, and the counter finally hit 1 million requests per second. We didn't hit the mark by finding a better hard drive, we hit it by changing the physical state of where the data lives. Handling 1 million requests per second is less about the price of the hardware and more about how that hardware is utilized. This volume of traffic requires architecture that anticipates and mitigates physical bottlenecks. At this scale, software engineering becomes a constant negotiation with physics and economics. You aren't just writing code, you are managing the bandwidth of network cables, the retrieval speed of RAM, and the mathematical efficiency of your searches. True scale is not something you can buy off the shelf. It requires fundamentally outsmarting the physical limits of the machine.